Let's talk about potential energy. The symbol I use for potential energy is U. And recognize that there's things called conservative and non-conservative forces. So the list of conservative forces basically is gravitational force. And there's two forms of that. If the acceleration to gravity is constant, we can go with mg. Or generally, if you're close to the surface of a planet, you would use mg, although that's when g is generally well known. And then there's the more generalized formula, g m1 m2 over r squared. There's also ideal elastic, and that force is equal to k delta x. I'm ignoring the signs right now. These are just magnitudes. So from the first semester course, those are the ones you're dealing with. Now officially, the definition of a conservative force is that if you have an object that goes through a round trip, so an object starts here, it goes somewhere, comes back to the exact same spot. If the change in kinetic energy is 0, then if that is the only force acting on it, it is a conservative force. The definition becomes a little bit hazier when you start dealing with the force that's constantly changing, but it still works. There's a calculus-based definition of it. Non-conservative forces would cause a change in energy. Conservative forces do not cause change in energy. That's why they are called conservative, because they conserve energy. This would be in the course Physics 151. In 152, we now have a new conservative force, and that is electric force. The electric force, kq1 q2 over r squared. It looks very similar to the gravitational force right there. Now, for every conservative force, there is a potential energy formula. Thus, if ever asked what's the formula for potential energy, the proper response is which one. If the gravitational force can be characterized by mg, then the potential energy formula is mgh plus some constant. So let me just put plus c here to represent, you can always add a constant to any of these. If you're using the generalized formula, then it's negative big G mass 1 mass 2 over r. If it's k delta x, then it's 1/2 k delta x squared. K is the spring constant. And if it is this, notice the similarity between these two. We do have a very similar formula here. It's kq1 q2 over r. The minus sign is not there because the gravitational force is always attractive and mass is always positive. You'd need to throw the negative in there. But this is attractive when the signs are opposite, and so the minus sign will pop into one of the two charges right here. But this, for this course, is the electric potential energy formula that we will know and love. Of course, you're going to love it. It's physics. But that's where we're going in right there. There is another video where I actually do the proper derivation of it, but it involves calculus, which is beyond the scope of this course. If I remember, I will put it link into Blackboard so that you have the option of seeing it.